Next up is drawing the structure of the dipeptide alanine serine at pH 4.5. So again, this is going to involve being able to determine what a side chain looks like at a certain pH, as well as focusing on the important concept of what a peptide bond looks like and how you take two free amino acids and you turn them into a dipeptide. So again, we're going to start by looking up the structures of our alanine and our serine, and also because we are given a particular pH, we want to know what the protonation state is of any ionizable groups or functional groups that can change their protonation state. So we'll need to look up pKs. So when we look those up from the data sheet, we have, this is alanine at pH 7, and this is serine at pH 7. All right, so we're interested in pH 4.5. So let's draw the structure of the dipeptide before, and then just based off of these two things, and then we'll figure out, do I need to change the protonation state of any of my groups, okay? All right, so I'm going to start, always when I draw a dipeptide, I'm going to start by drawing just the backbone, because it always looks the same as we mentioned in class, right? So I'll put a little alpha by the alpha carbons so that we can distinguish those, okay? All right, so we have 2 alpha carbons, and that's what our backbone looks like, okay? So now I'm going to add in the side chains, and I'm just going to make those different colors so it's easier. So the first one is alanine, right? So that is going to be a methyl group for the side chain. Second one is a serine, and its side chain is going to have a methylene and a hydroxyl group at the end of the side chain. All right, so the last thing to do, so let's write in our steps. 1, draw backbone first. Okay, part 2 is draw side chains. And then the last thing that we're going to do is we're going to check the protonation states. Of ionizable groups. So for the sake of clarity, I am going to circle the ionizable groups that remain in this molecule, or highlight them. Let's do that. Okay, so here we have our alpha amino group from the alanine. Okay, when we go and we look at the peptide bond, remember that the carboxyl and the amino groups that react to form the peptide bond are no longer ionizable. So this group right here, okay, is an amide bond. It is peptide. The peptide bond is what's known as an amide bond. So it is not ionizable. Okay. Now when we go over here, we've got our carboxyl group. Okay, and the carboxyl group also remains ionizable. If we look at alanine, its side chain doesn't have a pK associated with it, so we don't have to consider that. But serine, although it's very high, it is possible to deprotonate it, so we're going to circle that as well. And now what we're going to do is we're going to compare at pH 4.5, what's the protonation state of my group. Okay, so we're going to start at the left. So pH 4.5 is, if we look at the alpha amino for alanine, is 9.7. So pH 4.5 is, many units below the pKa of 9.7 for this group. Thus, the group remains protonated. All right, so this group stays protonated, and that's what it looks like, okay? Okay, so the next group, as we go, let's go to the R group on the serine, okay? So pH 4.5 is many units, many units below the pK of about 13, so group remains protonated. So that's good news for us. We don't have to change either of those. So now let's look at the carboxyl, okay? So we've looked at this and this. So now we have a serine alpha carboxyl group. The serine alpha carboxyl has a pK of 2.2. So the pH of 4.5 is, how does that compare to 2.2? It's, 2 units, at least 2 units above, 2 plus units above the pK of 2.2. So here it's above, so group is deprotonated. And we drew it in the deprotonated form when we started drawing the peptide. So this structure that we've drawn right here is the correct structure of the dipeptide at pH 4.5. Okay? So below, above pK. So this is the correct structure. Okay, so the second problem we're going to look at in this video is another one that deals with amino acid properties and isoelectric point, but this is looking at the isoelectric point for a protein. So it's going to be, a large molecule, and we're only changing one amino acid side chain in it from arginine to leucine. So first thing we're going to do, look up the data. Okay, so here we have our arginine. Here we have our leucine. Okay, and so what we're wondering is this going to have an effect on the isoelectric point of the protein? Okay, and if so, what would that effect be? Okay, so let's look at our data. Okay, so our arginine is one of our positively charged amino acid side chains, and it does have a pKa value. Okay, and we're changing it to leucine that has a non-ionizable side chain. If we look at it, it's a hydrophobic side chain that just has a bunch of some methylenes and a couple of methyl groups on it. Okay, so we are fundamentally changing from a positively charged amino acid to a neutral amino acid. Okay, so will this have an effect on the isoelectric point? So since the isoelectric point is defined by the fact that the molecule has functional groups that change their ionization state when you're moving around on the pH scale, then changing the nature of the side chain to something that is neutral and is not affected by pH is going to affect the isoelectric point. So thing number one, the pi will be affected. Okay, so that gets rid of will not change. Okay, and we do have the pKa values for the amino acids, so we do have enough information given to determine the answer. So now it is just would the pi increase or would it decrease? Okay. So let's look at what that pKa value is. So the pKa value is 12.5. Okay. So we've changed from a group with a very high pKa to a neutral side chain. Okay. So if we're getting rid of a very high number in our pKa calculation, remember that a PI is calculated by averaging pKa values. So if I'm getting rid of a high pKa, okay, so if I eliminate a high pKa group from my molecule, then the calculated PI value that I get is actually going to go down. Okay. Go down. So that's a decrease. So for this one, okay, my isoelectric point would decrease. Okay. Oops. So if I were changing, let's say, a glutamic acid to a leucine, so glutamic acid has an acidic group on its side chain with a very low pKa, and so that is going to be, that would be getting rid of a low value that I'm using in the average, and so that would mean that my PI would increase. Okay, so I'm going to stop here and make a video, separate video for secondary structure.